we'll cut formal inroads into calculus from this point onwards. Uh, we spent a full year trying to use things without understanding too much of it. We had a laymanish approach towards calculus beginning of class 11 because that was the best possible thing we could do at that point of time. That was a compromise, a very big compromise. But nevertheless, that's how you learn things. You have to go back and forth, back and forth. Eventually, at the end of the milestone, you know, things will begin to converge and they will appear holistic. Even now, while we dwell into digressions on calculus, we will still go back and forth, but the swings will not be as wild as they were earlier. Of course, by this time, you know, you've already bred familiarity with some basic differentiation, basic integration, etc. But then, you know, your exposure to variation, your exposure to in-depth understanding of things has been very limited. But that's all right. That's how it is most of the time. Now, my objective in the class today, since you know we'll be taking to this journey with greater intent and with higher intensity, it then becomes important for me to set the ground ready for you so that you know you can assimilate those ideas. So it starts with building the, well, with giving you a little bit of knowledge of the vocabulary of the language, right? So essentially vocabulary of the language, which means certain basic ideas which may not be part of the core aspects of calculus, but would be used every now and then like staple food. Now, essentially, you know, all forms of learning, mathematics, sciences, technology, humanities, etc., you know, in terms of the models that they follow, they involve similar looking functions, similar looking entities, of course applied to different things. When I talk of entities, it means the functions that we are dealing with. So, in the first place, you know, just to formally categorize functions for you, bless you, you know, there are these algebraic functions. Purely algebraic functions, which are meant to describe certain things, no matter where, they're meant to describe certain things. So when I talk of algebraic functions, we have, say, polynomials, ratio of polynomials, which are rational functions, ratio of polynomials, which are rational functions. In a polynomial, of course, powers of x are integral, are natural numbers. In fact, are whole numbers. They could be 0 also. 0, 1, 2, 3 are powers of x in a polynomial. We could have an algebraic entity in which powers of x are non-integral. They could be fractional, etc., and so on and so forth. Those are irrational functions. Those are irrational functions. Then a special case of polynomial would be a constant function, y equal to a constant, right? One whose value does not depend on an independent variable x, right? So these are algebraic functions, right? And then we have learnt a little bit of what we refer to as transcendental functions. the exponential function y equal to fx is e power x is a transcendental function, and the graph of e power x is like this. This is the graph of y's e power x. As x tends to minus infinity, y tends to 0. As x becomes larger and larger and larger, y will become larger and larger and larger. This is y's e power x, right? This is one kind of a transcendental function. Then we have y is log x, which is defined for x greater than 0 only, which is defined only for x greater than 0. The graph of y equal to log x is like this. At x equal to 1, it becomes 0. As x comes closer and closer and closer to 0, log x comes closer and closer and closer to minus infinity, minus infinity. No part of the graph exists to the left of the y-axis because log x is not defined for negative values of x. This is another transcendental function, log x. And then we have some of these trigonometric functions. Say y equal to sine x. Zero, pi, 2 pi, minus pi, minus 2 pi. This is the graph of y equal to sine x, right? Then we have y equal to cos x. Which is symmetric about the y-axis, at x equal to pi by 2, minus pi by 2, x equal to 3 pi by 2, minus 3 pi by 2, 5 pi by 2, minus 5 by 2, it's going to vanish, right? This is the graph of y equal to cos x. And then we have y equal to tan x. In the interval minus pi by 2 to plus pi by 2, this is the graph of y equal to tan x. Then again, this interval is of length pi, and the same graph gets replicated over identical lengths across the real number line, across the x-axis. So this is pi by 2, then there is 3 pi by 2, right? And halfway between them, which is 2 pi, it's again going to vanish. It vanishes at 0, rather pi. And so on and so forth. So the same graph gets replicated again and again, again and again, right? At x equal to pi, and so on and so forth. This is the graph of y equal to tan x. Similarly, we'll be able to draw the graph of sec x, cosec x, cot x, and so on and so forth. So these were some of the things with which you already have some basic familiarity, right? You have some basic understanding of these transcendental functions and some algebra associated with these transcendental functions. So what is it that you don't have? Now we have functions that are described piecewise. Functions that are described piecewise. These would be the functions on which I would focus today, because you've had some notion of some of these, but not a very comprehensive notion of some piecewise describers. For example, we'll look at length, modulus function, greatest integer function, fractional part of x. These three functions, we would look at length in the class today, and you would understand why I refer to these functions as piecewise functions. All right. These functions would constitute a very integral part of our journey in calculus. Every now and then they would surface, they would appear, and therefore good, nice, solid familiarity with the algebra associated with this function, with the graphs of these functions, properties of these functions is not a luxury, it's a necessity. Right? Now to begin with, let me take the modulus function. Let me take the modulus function. Can I wipe this off? Now, the moment I say mod x and x is a real number, the moment I say mod x and x is a real number, I actually mean mod x means distance of x from the origin. Mod x actually means distance of x from the origin. Where x is any number on the real number line. So we have the real number line with the origin being here. Numbers on this side of the origin would be positive numbers. Numbers on this side of the origin would be negative numbers, right? If x is located here, then distance of x from the origin is this. And this distance d is mod x, right? Say this is the origin. And I have a number which is, say, x equal to 5.1. Then what is the distance of x from the origin? 5.1 units, right? So mod x would be 5.1. If x is minus 3.2, what is distance of x from the origin? Mod x is going to be 3.2, right? Which means, and if x coincides with the origin, what is the distance of x from the origin? 0. So mod 0 will be 0. One way or the other, since mod x represents distance of x from the origin, it will never be negative. It will never be a negative number. This will always be greater than or equal to 0. Yes or no? If somebody says mod x is 3, it means x is a number such that its distance from the origin is 3. How many numbers are there whose distance from the origin is 3? 2 numbers. What are they? Plus and minus 3. So this would be x equal to plus 3 and minus 3. Right? In a general sense, if I said mod x is a, where a is non-negative, because the output of this operation can never be a negative number. The moment I say mod x is a, it means distance of x from the origin is a, right? A is a non-negative number. Then what can you say about x? X will be plus a or minus a, because x equal to plus a is a units away from the origin, x equal to minus a is a units away from the origin, which would mean x could be plus a or minus a. Yes or no? Suppose I said x is such that mod x is less than 3. That means x is such that its distance from the origin is less than 3. Now this is the origin. This is x equal to plus 3. This is x equal to minus 3. That means x cannot be to the right of 3, because then its distance from the origin will be larger than 3. X cannot be to the left of minus 3, then its distance from the origin will be greater than 3. So x has to float between minus 3 and plus 3. Of course, since 3 is not included, to the exclusion of minus 3 and plus 3, x would float in this interval. Yes or no? That means this would mean x must be less than 3, greater than minus 3. Yes or no? So in a very general sense, if mod x is less than a, where a is a positive number, if mod x is less than a, where a is a positive number, I can conclude that x must be less than a but greater than minus a in general. And if mod x is less than or equal to a, I can conclude that x must be less than or equal to a, greater than or equal to minus a. Very ordinary, right? Now, can I wipe this off? Suppose I said mod x greater than 5. It means x is such that its distance from the origin is more than 5 units. Look at the origin. This is 5. This is minus 5. Obviously, x could lie to the right of 5, in which case its distance from the origin will be greater than 5, right? X could lie in this region, or x could lie to the left of minus 5, then also its distance from the origin will be more than 5 units, right? But x cannot float between minus 5 to 5, because then its distance from the origin will be less than 5. So mod x greater than 5 means x greater than 5 or x less than minus 5. This is what it means. X greater than 5 or x less than minus 5. Yes or no? And in a very general sense, if I said mod x greater than a, it would, where a is a positive number, it would mean x greater than a or x less than minus a, if a is positive. But if a is negative, then mod x greater than a, all values of x. If a is a negative number, then a positive number, a non-negative number will always be larger than a negative number. So if a is a negative number, mod x greater than a will be true for all real values of x, right? And one of the things that I mentioned to you way back, and it makes sense to reiterate this, root of x squared is never a negative number. Root of x squared is not x. Root of x squared will always be mod x. And mod x will cause this entity to never be negative. Root x squared can never be negative. I mean, if somebody says root minus 3 squared is minus 3, then this is wrong. It is mod minus 3 and will always be 3. You know what I'm saying? Clear? See, when I have an equation like this, x squared is 9, and I solve this equation, then what is it that I write? I write plus minus root 9, isn't it? Why? Which really means that root 9 will only be 3. And the value of x can be plus or minus 3. But root 9 is always 3. Output of this will never be a negative number. You know what I'm saying? Root minus 3 whole squared would be mod of minus 3, which will always be 3. So if I said root of x minus a whole squared, this is going to be mod x minus a. mod x minus a, right? Can I wipe this off? Now, graphically, y equal to fx equal to mod x. Now, what is this operator mod doing? It's producing an output which is non-negative. That is what it's doing. So if the number inside is already non-negative, then the output is the number itself. If x is already non-negative, then the output of mod x will be x only. That means it's going to be x if x is greater than or equal to 0. No issues. Then the modulus will not have to perform any operation. But if the quantity inside is negative, if x is negative, then it can't throw an output which is x. The output of this operation can never be negative. Then mod x will be minus x. Mod x will be minus x when x is negative. So that if x is negative, minus x will be positive. So when x is greater than or equal to 0, mod x, y equal to mod x is x, and is minus x when x is less than 0. Yes or no? Graphically, then the graph of y equal to fx is mod x for x greater than or equal to 0, y goes as the straight line x. Y equal to x is the straight line passing through the origin and makes an angle 45 degrees with the positive direction of the x-axis. Slope of this is 1, right? And when x is less than 0, it goes as y equal to minus x, which has a slope m equal to minus 1. So this is the line y equal to x. This is the line y equal to minus x. This is the graph of y equal to mod x. These two lines are perpendicular to each other. At x equal to 0, there is a behavioral change in mod x. There is a behavioral change in mod x. We'll analyze this behavioral change mathematically, but as of now, pictorially, you can see that at x equal to 0, there is a sudden change in character. To the left of 0, it was going like y equal to minus x, and from 0 onwards, it went like y equal to x. So there was a change of character at x equal to 0. Yes or no? Right? If I had, and that's what I meant by a piecewise description. So this piece of the graph is one, and this is another piece. In a certain sense, there is a fundamental change in character. There is a fundamental change in character at x equal to 0. What that means is a matter of greater description. We'll come to that later. But you can witness with the white of your eyes that at x equal to 0, there is a change of character. There is a piecewise description of this function. For x greater than or equal to 0, the description is x. For x less than 0, the description is minus x. Right? If I had, say, y equal to fx equal to mod of x minus a. Mod of x minus a is any real number. Then, if x is great, see, if the quantity inside is non-negative, then the output of this operation would be the quantity itself. That means, if this will be equal to x minus a, will be equal to x minus a if x is greater than or equal to a. Because if x is greater than or equal to a, x minus a is non-negative, right? And when x is less than a, then x minus a is a negative number. The output cannot be x minus a. The output is minus of x minus a. So this will become minus of x minus a. That is a minus x when x is less than a. That means now graphically mod of x minus a at x equal to a, it will become 0. At x equal to a, mod of x minus a becomes 0. Right? To the right of A, it goes as the line y equal to x minus a, which is a straight line with slope 1, right? To the right of A, it goes as y equal to x minus a. To the left of A, it goes as a minus x, which is slope minus 1, right? To the left of A, it goes as a minus x, y equal to a minus x. That means mod of x minus a changes behavior at x equal to a. To the left of A, it was going along this line y equal to a minus x. To the right of A, it went like y equal to x minus a, right? Piecewise, which is what I meant by piecewise description. Yes or no? And no part of this graph can be below the x-axis, because y, which is mod of x minus a, the output of this operation, no matter what x is, can never be negative. So y can never be negative. So no part of this graph will be below the x-axis. No part of this graph will be below the x-axis. Yes or no? Are you all fine with this? Now, another way of looking at it. So if I said mod of, say, a minus b, then that's going to be a minus b if a is greater than or equal to b, and is going to be b minus a if b is greater than a. That means a is less than b, right? All of you understand this. Now, another way of looking at things. X could be positive, negative, or 0, right? I can look at the following. Mod x, I claim, mod x, I claim mod x, I claim is larger, maximum, larger of xn minus x. This operation means max of x comma minus x means of these two numbers, select the one which is larger. Between x and minus x, this operator will filter out the larger of these two numbers. And the larger of these two numbers would be mod x. Because between x and minus x, the one which is positive will be larger, the one which is negative will be smaller. We do not know which is positive, which is negative between these two, right? That will depend on the sign of x. But no matter what, the larger of these two numbers will be positive, would be non-negative, and will therefore represent mod x. That's another way of looking at mod x. Mod x is larger of max of x comma minus x means larger of x and minus x. Yes or no? Are you all fine with this idea? Now, if I have two real numbers x and y, if I have two real numbers x and y, yeah, ask questions. You have a question, right? So suppose I have two real numbers x and y, then I claim that the larger of these two real numbers between x and y, one of them will be larger and the other one, let's say, will be smaller, assuming they are unequal. The larger of these two real numbers would be the following, I claim. Suppose between these two real numbers, say x is larger, right? Say x is larger. Then the output of this operation should be x, right? Now, if x is larger, then mod x minus y will either be x minus y or y minus x. But x minus y is positive here, right? So mod, if x is larger, that means x is bigger than y, then mod of x minus y cannot be y minus x. It has to be x minus y. Yes or no? And then this number becomes x plus y by 2. The output of this operation is x minus y by 2 if x is larger, giving me x. Yes or no? Right? No? Suppose y is larger, then the output of this operation should give me y. The output of this, You can see this is x plus y by 2, and then mod of x minus y cannot be x minus y, because x minus y is negative if y is larger. So it should be y minus x. So this is y minus x by 2, which is y. Do you understand this or you don't understand this? Larger of two real numbers, if you have to compare two real numbers, perform this operation. The output of this will give me the larger of the two real numbers x and y. Yes or no? Isn't it? And similarly, I claim that smaller minimum means smaller of two real numbers x and y would be x plus y by 2 minus mod of x minus y by 2. You want to check it out yourself. The larger of two real numbers will be given by this operation. The smaller of two real numbers x and y will be given by this operation. Guaranteed. Useful result to know and easy to check. Easy to check, right? Can I wipe this off? Okay. Suppose x and y are two real numbers. Any two real numbers. Can I say x cannot exceed mod x? At best, x could be equal to mod x. Right? If x is negative, x will be less than mod x. Because mod x is positive, but x is negative. And if x is positive, x would be equal to mod x. Yes or no? So x is less than or equal to mod x. Can I say this? No matter what the sign of x is. Similarly, can I say y will be less than or equal to mod y? Can that be said? Now if I add these two, x plus y will be less than or equal to mod x plus mod y. Can this be said? Right now? Okay. Now, can I also say this? Minus x also cannot exceed mod x. If x is negative, at best, minus x will be equal to mod x. Right? Otherwise, if x is positive, minus x will be a negative number and mod x will be a positive number. So can I say minus x less than or equal to mod x? Right? Similarly, can I say minus y less than or equal to mod y? Can this be said? Minus y less than or equal to mod y. Can I say that? Now if I add these two, minus of x plus y less than or equal to mod x plus mod y. Yes or no? If I add these two, minus of x plus y is less than or equal to mod x plus mod y. Yes or no? Right? Now, okay, from what we did I tell you mod x is maximum of x comma minus x is larger of x and minus x. That's mod x. So can I say mod of x plus y? Mod of x plus y is larger of x plus y and minus of x plus y. Can I say this? Larger of these two. Can I say this? Mod of x plus y will be larger of these two numbers? Hey, but no matter which of the two is larger, even the larger number is less than or equal to mod x plus mod y? Yes or no? Right? X plus y is less than or equal to mod x plus mod y. Minus of x plus y is also less than or equal to mod x plus mod y. So no matter which of the two is larger, this or this, mod of x plus y cannot exceed this mod x plus mod y. Yes or no? Are you all fine with this? Which means we come to a very pertinent inequality, mod of x plus y less than or equal to mod x plus mod y, which is called the triangle inequality, This is true in complex numbers also. If z1 and z2 are two complex numbers, mod of z1 plus z2 will be less than or equal to mod z1 plus mod z2. Right? And one thing which I would urge you to check on your own is the following. Like I said, mod of x plus y less than or equal to mod x plus mod y. The question is when are the two equal? That means when mod of x plus y will become equal to mod x plus mod y. If and only if, IFF means if and only if x and y are of the same sign. Which means x into y is greater than 0, say. Both negative or both positive. And of course also when say one of them is 0, then also we exclude that case, so those are trivial cases. But if none is 0, then and if x into y is positive, that means both positive or both negative, then this equality occurs. But if they are of opposite signs, if x into y is less than 0, then mod of x plus y will be less than mod x plus mod y. If xy is less than 0, that means x and y are of opposite signs, then mod of x plus y will be less than mod x plus mod y. Suppose I say mod of x squared minus 1 is equal to mod of x squared plus x minus 3. Suppose I say this and I ask you a question, for what intervals of x will this be true? For what intervals of x will this be true? Hey, look at this. This is mod of some x, this is some mod of y, and do you realize x plus y is this? X square plus x minus 3. That means it turns out that mod x plus mod y is equal to mod of x plus y. That can happen only if x and y are of the same sign. That can happen if x squared minus 1 into x minus 2 is greater than 0. Which means this can be written as x plus 1 into x minus 1 into x minus 2 is greater than 0, right? Now wavy curve method, minus 1, 1 and 2. From wavy curve method, what is the interval in which this is greater than 0? X greater than 2. X lying between minus 1 and 1. Union x lying between minus 1 and 1. Yes or no? Right? These are the intervals, x greater than 2 and x lying between minus 1 and 1. This product will be positive from wavy curve method. All of you recall wavy curve method, right? If not, go back to my bridge course DVD, in which I have given a reasonable count, account of the wavy curve method. Take a look at it. Those of you who don't have the bridge course DVD, pick it up from the office and then take a look at it, right? Now, some important transformations related to the modulus function. Some very important transformations related to the modulus. Have I confused you in any sense? No. Say, somebody gave you the graph of y equal to fx. Somebody gave you the graph of y equal to fx. Say this was the graph of y equal to fx. Then, what is the graph of y equal to minus fx? What is the graph of y equal to minus fx? Okay, very clearly, break it up into two parts. Say this part, for example. If you took the minus of this, it will become this. Yes or no? Right? Look at this. If you took the minus of this, it will become this. Yes or no? Say this is say y equal to fx, then y equal to minus fx will be like this. Yes or no? Which is what? The mirror image of fx about the x-axis. Yes or no? If for any given x this is fx, then this would be minus fx. Yes or no? This is the graph of y equal to minus fx. So, if you have to grow from y equal to fx to y equal to minus fx, what would you do? You will create a mirror image of the graph of fx about the x-axis. So, the graph of y equal to minus fx will turn out to be like this, right? I'm so sorry. I'll just redraw this. The mirror image of this, and then the mirror image of this, which is this. Yes or no? Right? This is x equal to x1. The mirror image of the positive part about the x-axis is this. The mirror image of the negative part about the x-axis is this. This then is the graph of y equal to minus fx. Yes or no? Reflect the entire graph about the x-axis, you get the graph of y equal to minus fx. No confusion on this, right? Now, reason I said this, suppose this is the graph of y equal to fx. I now want to be able to draw the graph of y equal to mod of fx. I now want to be able to draw the graph of y equal to mod of fx. Given the graph of y equal to fx, I wish to draw the graph of y equal to mod of fx. So, very clearly, look at this. Y is mod fx, by definition, is going to be equal to fx whenever fx is greater than or equal to 0. Right? That means the graph of mod fx and fx will be identical as long as fx is non-negative. That means this part, x1 onwards, fx and mod fx will be identical, because to the right of x1, so this happens for x greater than or equal to x1, fx is greater than or equal to 0. So the graph of whatever mod fx gives as y is the same y given by fx. So the graph of y equal to mod of fx and fx will be identical for fx greater than or equal to 0. That means for that part of fx which lies above the x-axis. That means now for x greater than or equal to 0, there would be the graph of mod fx and the graph of fx will become identical. But when fx is less than 0, when does fx become less than 0? When x is less than x1. When x is less than x1, fx is negative, so mod of fx will not be fx, will be minus fx, will be minus fx. That means if this is the graph of fx, the graph of minus fx will be the mirror image about the x-axis. That means whenever fx is negative, which happens in this case to the left of x1, reflect that portion about the x-axis so that you can get minus fx, reflecting that portion about the x-axis will give me this. Yes or no? Reflecting this portion about the x-axis, right, will roughly be like this, which is what you see here. Yes or no? To the left of x1, for any given x, this is y equal to fx. So what would be y equal to minus fx? This will be y equal to minus fx. Minus fx will be this. Yes or no? If this is fx, then minus fx will be this. Right? Are you confused? No? So, given the graph of y equal to fx, right? Notice where fx changes sign. In this case, fx changes sign at x1, right? So the portion of the graph above the x-axis will be retained, but the portion below the x-axis will get reflected about the x-axis. Yes or no? Just make a formal note of it. In order to migrate from y equal to fx to y equal to mod of fx, in order to migrate from y equal to fx to y equal to mod of fx, retain the portion of fx, which is not below the x-axis, the portion below the x-axis, the portion of fx below the x-axis needs to be reflected about the x-axis, to get the graph of y equal to mod of fx, And interestingly, see, y equal to fx, for example, there was no change of behavior anywhere, right? But the moment you took y equal to mod of fx, then there was a characteristic change brought about at x1, right? To the left of x1, it behaved like one way, and to the right of x1, it behaved another way. Yes or no? So the moment you take modulus, you are in a certain sense inducing and inviting change of character, change of behavior of the function. Yes or no? However, if there is a function which is never negative, this is the graph of y equal to fx, and this function is never negative, then the graph of mod of fx will also be the same all along, right? All's good, right? Say, for example, y equal to log x. This is the graph of y equal to log x. At x equal to 1, it becomes 0. I now want to be able to draw the graph of y equal to mod of log x. Wherever log x is positive, it will be retained. 1 onwards, it's going to be retained as such. To the left of 1, log x is negative, so reflect this portion about the x-axis. This then will be the graph of y equal to mod of log x. Right? Suppose I have a parabola y equal to x squared minus 5x plus 6. It's a quadratic with roots 2 and 3, upward opening parabola, right? Its graph would be like this, with roots 2 and 3. Now what I want to do is y equal to mod of x squared minus 5x plus 6, mod of fx. Then to the left of 2, it's above the x-axis, I will retain that. To the right of 3, fx is non-negative, I will retain that. Between 2 and 3, fx is becoming negative, I will flip this portion about the x-axis, reflect this portion about the x-axis. This will give me the graph of y equal to mod of x squared minus 5x plus 6. Yes or no? Clear? In fact, just trivial, but y equal to x is the straight line, yes or no? Y equal to mod x. Retain this because it's not below the x-axis. This one reflect about the x-axis. This is the graph of y equal to mod x. Yes or no? No? Right? Say say I have in the interval 0 to 2 pi y equal to sin x in the interval 0 to 2 pi. And I wish to draw the graph of y equal to mod of sin x. Do this. 0 to pi, retain it because it's not below the x-axis. But pi to 2 pi, reflect this frame about the x-axis. This is the graph of y equal to mod of sin x. Right? So far so good, right? So far so good. Can I wipe this off? Suppose I have the graph of y equal to fx. Now this is what I seek to do. I have the graph of y equal to fx. From this, I want to draw the graph of y equal to f of mod x. You know what I'm saying? Not mod of fx, f of mod x. Given the graph of y equal to fx, I now wish to trace the graph of y equal to f of mod x. Let's see. Give me some time to teach. You will no. There is some more here than what you're just imagining. So Say this is the graph of y equal to fx. I now want to trace from this the graph of y equal to f of mod x. Now, do you realize that this will be the same as fx when x is greater than or equal to 0? Because when x is greater than or equal to 0, mod x is x. Yes or no? But when x is less than 0, this will be f of minus x. This will be f of minus x. Mod x will be minus x. This will be f of minus. Not minus fx. F of minus x. Right now. Which means, to the right of the y-axis, the graph of f of mod x and f of x is the same. To the right of the y-axis, f of x and f of mod x will be the same. The output produced by f of mod x will be the same as the output produced by f of x. Right? So this part is retained to the right of the y-axis. Are you there with me, all of you? Huh? Oh, they don't look the same because, you know, but they're actually the same. This part and this part. It's meant to be the same. Right? Now, when x is negative, which part? What do I reflect? This part? No. That's the point. See, suppose x is minus 3. Then, what is the value of y at x equal to minus 3? X is a negative number, is f of 3. Yes or no? Put x equal to minus 3, f of 3. Say for example, this is x equal to 3, this will be f3. Huh? This is a point 3 comma f3. Right? This is 3 comma f3. X is 3, y is f3. Now, I want to draw y equal to f of minus x when x is less than 0. So, say at x equal to minus 3. X equal to minus 3 is a point here. Right? What's the value of y at x equal to minus 3? Is f of 3, which is the same as this. That means, on the graph of y equal to f of minus x, when x is minus 3, y will still be f3. You know what I'm saying? Which means, if 3 comma f3 is a point, then if x is minus 3, say this is 3 comma, this is 3, this is f3, which is a point on the graph of the f of mod x, means f of 3. Is this is a point on the graph 3 comma f3, right? F of mod 3 is the same as f3, which is this length, because this is anyways identical. When x is minus 3, y will be still plus f3. That means f of 3 is this length. When x is minus 3, y will still be f3. Yes or no? When x is minus 2, what is the value of y? f2. Which, now, this was a point here on this part, right? What was this? Mirror image about the y-axis. That means every point here will be mirrored about the y-axis. Isn't it? If this was the graph to the right of the y-axis, then every point here will be mirrored about the y-axis. Yes or no? And the mirror of this about the y-axis will be like this. Yes or no? Rahul, you are confused? No? Yes, this part no matter. It could have been anything. It didn't matter. It didn't matter. Only this part will be retained and it will be reflected about the y-axis. Absolutely. Absolutely. Yes. make a formal note. Given the graph of y equal to fx, given the graph of y equal to fx, to migrate to y equal to f of mod x, to migrate to y equal to f of mod x, retain the portion of the graph y-axis onwards to the right of the y-axis, y-axis onwards to the right of the y-axis, and reflect the same about the y-axis, and reflect the same about the y-axis. So this is the graph of y equal to fx. If you want to draw the graph of y equal to f of mod x, retain this portion and reflect this portion about the y-axis. Together it will give you the graph of y equal to f of mod x. Can I wipe this off? Only the y-axis. Only this part, one to the right of the y-axis, will get reflected. This part then does not matter. This part could have been something else also. For example, this part could have been, say, like this. It didn't matter. It didn't matter. Only this portion will get reflected about the y-axis, that far and no further. Quadrant does not matter in this case. To the right of the y-axis and to the left of the y-axis. That's all. See, for example, okay, fourth quadrant, if the graph lies in the fourth quadrant, what do I do? Say, for example, say this is y equal to fx. Say this. This is what you're saying, fourth quadrant. Nothing, same thing. This portion to be retained and forget all about this and to be reflected about the y-axis. This is what you do when you go from y equal to fx to y equal to f of mod x. Have I confused you? Then let me try harder. All's good, right? Huh? Clear, no? Say, y equal to, say, log x. This is the graph of y equal to log x. Now I want to draw log of mod x. Mod x. I will retain this portion, right? Retain the portion to the right of the y-axis and reflect the same about the y-axis. So if this will be plus 1, this will be minus 1. Retain the portion to the right of the y-axis and reflect the whole thing about the y-axis. That will give you the graph of y equal to log of mod x. And realize that even though log x is defined only for x greater than 0, log mod x actually is defined for x less than 0 also, because mod x will anyways be positive. Right? So the domain of description changes when you go from log x to log mod x. In this case, the domain itself changes. In this case, the domain was only x greater than 0. Now the domain is except x equal to 0, all x is included in the description of this function. Yes or no? Suppose 2 and 5 are the roots, right? This is the graph of this. Alright. Mod of x. X to be replaced by mod of x. I want to draw the graph of mod x squared, replacing x by minus 7 mod x plus 10. I want to draw the graph of this. I will retain this portion. To the right of the y-axis, I will retain this portion, 2 and 5, and reflect this portion about the y-axis. Yes or no? Huh? Right? Now, suppose I take the modulus of this, then what do? Mod of this. Whatever is negative, I will reflect about the x-axis, because if I take the mod, no part can be negative. Y can never be negative. Isn't it? When you go from y equal to fx to y equal to mod of fx, all that you do is whatever lies below the x-axis, flip it about the x-axis and retain everything else. So this will become the graph of y equal to mod of mod x squared minus 7 mod x plus 10. That's the transformation that takes place. Right? Is that clear? Huh? Wipe this off? Huh? Suppose this is the graph of y equal to sine x, and you want to draw the graph of y equal to sine mod x. Retain the portion to the right of the y-axis, right? And reflect this portion about the y-axis. Reflect this portion about the y-axis. This is the graph of y equal to sine mod x. If I took mod of sine mod x, then wherever it's negative, flip that about the x-axis. Then I'll get the graph of mod of sine mod x. Yes or no? All's good? Now, another transformation. So we've learned two transformations already, from y equal to fx to y equal to mod of fx. Y equal to fx to y equal to f mod x. Now the transformation that I'm going to teach you is, given y equal to fx, I want to draw the graph of mod y equal to fx. I want to be able to draw the graph of mod y equal to fx. From y equal to fx, I want to be able to move to mod y equal to fx. Okay. Say this is y equal to fx, right? Now, there is a region in which fx is positive, right? There are some values of x for which fx is positive, and there are some values of x for which fx is negative. Yes or no? Some values of x, there is part of the graph above the x-axis, there is part of the graph below the x-axis. Now, whenever fx is negative, can I find a y such that mod y is a negative number? Whenever fx is negative, that means for this x, can I find a y such that mod y is negative? No, I can't. Can mod y ever be negative? Right? That means to the left of alpha, x equal to alpha, fx is negative, right? And whenever fx is negative, I can't find mod y equal to y such that mod y equal to fx. That means for mod y equal to fx, no part of this graph will exist to the left of alpha. No part of this graph will exist to the left of alpha, because to the left of alpha fx is negative and I can't extricate y from the equation mod y equal to fx for x being a negative number. Say this is x equal to x naught, right? F of x naught is less than 0, right? So can I find y such that mod y is f of x naught? Can I, f of x naught is negative? So can I find a y such that mod y is negative? No. Therefore, for all such x naughts to the left of alpha, I can't create a transformation from y equal to fx to mod y equal to fx. Tell me what is your concern here? No? That means this graph in this case will not exist in all those regions wherever fx is negative. Wherever fx is negative, no part of this graph will prevail. Right? Now, so to the left of alpha, x less than alpha, this graph is ruled out. Ruled out. For x greater than or equal to alpha, fx is, let's say x greater than alpha, for example. Fx is greater than 0. Say this is then mod y equal to fx, which is greater than 0, would cause y to be plus fx or minus fx. Will cause y to be plus fx or minus fx, isn't it? If mod y is 3, y can be plus 3 or minus 3. So if mod y is fx and fx is a positive number, y can be plus fx or y equal to minus fx. Yes or no? This is y equal to fx, right? Y equal to minus fx will be this. If this is y equal to fx, then a reflection of this about the x-axis will be y equal to minus fx. But mod y equal to fx would mean y could either be plus fx or y could be minus fx. That means the graph of mod y equal to fx will be this y equal to fx and this, which is y equal to minus fx. Yes or no? What? No? Sure, na? That means the graph of mod y equal to fx will look like this in this case. Y versus x, such y versus x such that mod y is fx will be y equal to fx like this, or y equal to minus fx like this. This is y is, all the y's here will represent plus fx, all the y's here will represent minus fx. Together they would constitute y mod y equal to fx. No? And no part of the graph will exist to the left of alpha. Write down. To migrate from y equal to fx to mod y equal to fx, to migrate from y equal to fx to mod y equal to fx, ignore and reject and discard anything that you like. Ignore the portion of fx where it's negative, where it's negative. The portion of fx which is non-negative, The portion of fx which is non-negative has to be retained, and its reflection about the x-axis, needs to be added. Its reflection about the x-axis needs to be added. Which means y equal to say sin x three pi say, right? And I want to migrate from y equal to sin x to mod y equal to sin x. What would I do? Wherever positive, I will retain and reflect. Wherever negative, I would reject. So this portion will be rejected. No part of the graph will exist between pi and 2 pi. But between 0 to pi, I will retain this portion and also reflect about this portion. Yes or no? Then between 2 pi to 3 pi, again, I'll retain and reflect. I will retain and reflect between 2 pi to 3 pi. This is what would happen. Sorry, let me just draw a better figure for you. 0 to pi, retain and reflect, because fx is non-negative. Between pi to 2 pi, forget. Between 2 pi to 3 pi, positive, so retain and reflect. And so on and so forth. This is the graph of y versus x such that mod y is sin x. Y versus x such that mod y is sin x. Got me? We've learned therefore three very important transformations. Y equal to fx to y equal to mod of fx. Y equal to fx to y equal to f of mod x. From y equal to fx to mod y equal to fx. Yes or no? Clear? So this modulus function was one piecewise description. Different intervals, there would be different characters perhaps. At some point, there would be change of behavior. Therefore, piecewise. The output of this operation, modulus operator, is a non-negative number, right? Obviously, mod of x will always be mod of x, because this is non-negative. Modulus of a non-negative number would be the number itself. Now there is another operation which produces integer outputs. There is another operation which will produce integer outputs. Now all real numbers can be broadly classified as integers and non-integers. Yes or no? All real numbers could be classified as either integers or they are not integers, right? That's one way of looking at it. So if let's say these are two consecutive integers, I and I plus 1 are two consecutive integers. I and I plus 1 say are two consecutive integers. if x is a number lying between, sandwiched between two integers, right? If x is greater than I but less than I plus 1, right? X is sandwiched between two integers, not an integer but sandwiched between two integers. Then this is the, and what are the other integers? To the left of I, the next integer would be I minus 1, I minus 2, and then this is going to be I plus 2, I plus 3, and so on and so forth. Now, if x is not an integer, then the integer to the immediate left of x is I. Then the integer to the immediate left of x is I. This I is called box of x. This I is referred to as box of x. This I is called box of x. If x, that means if this is x, then this would be box x. The output of this operation is an integer. What integer does it produce? It produces an integer to the immediate left of x. It produces an integer to the immediate left of x, right? If x is an integer itself, say I, then the output of this operation box of x will be I itself. The output of this operation would be I itself. If x is an integer, the output of box of x will be I only. If x is not an integer, then the output of this operation would be the integer to the immediate left of x, right? So one thing, see, x is either an integer or not an integer. If x is an integer, then box of x, say x is 0, plus minus 1, plus minus 2, these are integers, right? The output of this operation would be the integer itself if x is an integer I. Say if x is minus 3, then box of minus 3 would be minus 3. If x is 5, then this is an integer, this is going to be 5, right? But say if x is 5.1, this is box of x, x is 5.1. Then what are the two integers between which this is sandwiched? 5 and 6. Then this 5 is box of 5.1, is box of 5.1. The integer to the immediate left of 5.1 would be 5. Yeah. Then also this is the nearest integer to the left of 5.8, isn't it? So, yes. Why? Huh? Huh? Yeah, suppose x is minus 3.5, 3.4 say. Then there is going to be minus 4 and minus 3. Then this minus 4 would be box of minus 3.4. The integer to the immediate left of minus 3.4 would be box of minus 3.4. But box of minus 4 would be minus 4. Box of minus 5 will be minus 5. Box of 2 would be 2. Box of an integer would be the integer itself. But box of a non-integer, if x is not an integer, it must anyways lie between two integers. Then the box of this will be I, which is the integer to the immediate left of x. Nahin? Now, all's good, right? Very clearly, I minus 1, I minus 2, etc. are various integers to the left of x. Of all these integers, which is the greatest integer? I. Of all the integers to the left of x, which is the greatest integer? I. Right? So box x is also defined as the greatest integer less than or equal to x. Is also defined as the greatest integer less than or equal to x. Box x is defined as the greatest integer less than or equal to x. See, of all the integers to the left of x, the greatest is I, which is box x. greatest integer but not exceeding x. Box x at best can be equal to x. That happens when x is an integer. Otherwise, box x will always be to the left of x. So box x for sure is less than or equal to x. Box x is less than or equal to x. Right? And if this is x, then do you realize x minus 1 will lie somewhere here? 1 unit to the left of x. It will then float between I minus 1 to I. So do you realize box x will always be greater than x minus 1? Isn't it? This is box x. It will be greater than x minus 1. So box x less than or equal to x but greater than x minus 1 is a useful inequality. Box x less than or equal to x but greater than minus x. Right? Now, see, any integer and any real number, positive or negative, any real number, positive or negative, could be written as an integer plus a fraction f, where f could be greater than or equal to 0 but less than 1. X could be greater than or equal to 0 but less than 1. Yes or no? Then the integer to the immediate left of x will be I. Yes or no? Because if this is I plus 1, then this is f units, this is x. I plus f is x. This is x, right? So, very clearly, if x could be written as an integer plus a fraction greater than or equal to 0 but less than 1, then box of x will be I. Box of x will be I, algebraically speaking. Yes or no? Say if I have 5.6, this can be written as 5 plus a number lying between 0 and 1. I plus f, box of x. X is I plus f. Output of this operation would be 5. Suppose I had minus 5.6. Then this can be written as, look, the trap in which you could fall is minus 0.6. Now, minus 0.6 is not a number lying between 0 and 1. So, you would have to cause it to lie between 0 and 1, right? So, this is minus 5. What you do is add 1 to this. If you add 1 to this, this will become plus 0.4, right? But when you add 1 to this, you must subtract 1 so that the number retains its value. So, you subtract 1, this will become minus 6. This will then become minus 6. Then now it is I plus f, where f lies between 0 and 1. The output of this operation would be minus 6. Which is the integer to the immediate left of minus 5.6. Yes or no? Are you all okay with this or not okay? Say y equal to fx equal to box of x. I want to draw the graph of y equal to fx equal to box of x. Okay. Now, when x has any value between 0 and 1, right? Look at 0 and 1. If x floats from 0 to 1, including 0 but excluding 1, x is anywhere here, then box of x will be 0. If x is greater than or equal to 0, less than 1, box of x will be 0. Yes or no? Is 0. When x is greater than or equal to 1 but less than 2, box of x will be 1. When x is greater than or equal to 2 but less than 3, box of x will be 2. Similarly, if x is less than 0, greater than or equal to -1, box of x will be -1. Similarly, x less than -1, greater than or equal to -2, box of x will be -2, and so on and so forth. Right? Let's draw the graph of this. Let's draw the graph of this to understand its piecewise description. Right? Now, when x lies between 0 and 1, which includes 0 but excludes 1, which includes 0 but excludes 1. This is including 0, excluding 1. This is a kink. Kink means it does not include this point. This is a solid dot. This point included. This is a hollow dot. It's a kink. It does not include this point. So which says x greater than or 0, less than 1, fx is 0. Therefore, between 0 and 1, this is how it goes. Now, at x equal to 1, box x suddenly jumps to 1. When x becomes equal to 1, box x is 1. So x equal to 1, it becomes 1, and up to 2 it remains 1. Up to 2 it remains 1. So again, at x equal to 1, it becomes 1. It remains 1 all the way to 2. But at x equal to 2, it suddenly jumps to 2. Right? It suddenly jumps to 2 at x equal to 2 and remains 2 all the way to 3, excluding 3. Right? And then so this is y equal to 0, this is y equal to 1, this is y equal to 2, y equal to 3, and so on and so forth. Right? There is abruptness. There is change of character in this case. There is abruptness at x equal to 1. There is abruptness at x equal to 2. There is abruptness at x. Fellow was going fine as y equal to 2 all along. The moment it encountered 3, thoda ho gaya. Jump to 3. And then for a while it was steady at 3. It remained 3. But at 4, it jumped to 4, remained 4. Realize that? Now, to the left, x lying between -1 and 0, which includes -1 but excludes 0. It remains y is -1. So inclusion of the left end of the interval but exclusion of the right end of the interval. 0 is excluded but -1 is included. Y is -1. Yes or no? Then between -2 to -1, it remains -2. At -2, it is -2. Goes all the way till -1, and then it shows a jump. Remains -1, jump, and so on and so forth. This is the graph of y equal to fx equal to box of x. And every time the quantity inside is an integer, 0, plus -1, plus -2, etc., the graph exhibits abruptness, change of behavior, change of character. The description of this function is piecewise. The description of this function is piecewise. Where does it change character? Every time the quantity inside becomes an integer. Every time the quantity inside this operator is rendered an integer, there is change of behavior, there is change of character. Yes or no? And you see a series of steps here. You see a series of steps here. And therefore, because of the very looks of the function, sometimes it's also called a step function. Sometimes it's also called a step function. Box x or step function or greatest integer function. It's also called the greatest integer function, step function, and so on. Clear? Hmm? Can I wipe this off? Huh? All's good. Now, this function y equal to fx, box of x plus box of minus x, box of x plus box of minus x. Now when x is an integer, then output of this will be x, right? Minus x is also an integer, then the output of this will be minus x, and therefore it produces a 0. Every time x is an integer, it produces an output which is 0, right? Now when x is not an integer, if x is not an integer, it will be an integer plus a fraction f, where f lies between 0 and 1. Yes or no? Now, box of x plus box of minus x then is going to be box of I plus f plus box of minus x means minus I minus f. In this case, f is a number lying between 0 and 1. So the output of this operation is going to be I itself, right? Whereas in this case, minus I minus f is like minus I minus 1 plus 1 minus f. Yes or no? Minus I minus 1 plus 1 minus f. Now 1 minus f will be a number lying between 0 and 1. Yes or no? If f lies between 0 and 1, 1 minus f will also lie between 0 and 1. Yes or no? The output of this operation will not be minus I, because minus f is not a positive fraction. You have to convert this into a positive number lying between 0 and 1. That's the reason you add 1 to it. This will become 1 minus f minus I minus 1. So the output of this operation is going to be minus I minus 1. Yes or no? So plus minus I minus 1, and therefore minus 1 when x is not an integer, right? So when x is not an integer, the output of this operation is minus 1. Yes or no? When x is an integer, this produces 0. When x is not an integer, it produces an output which is minus 1. Yes or no? Now, this is an important property, huh? Take notice of this. Box of x plus box of minus x is 0 when x is an integer, and is minus 1 when x is not an integer, right? Now, look, if I is an integer, and if I said box of x is I, then do you realize box of x will be I for all values of x lying between I and I plus 1, which includes I but excludes I plus 1. So box of x is I would mean x must be greater than or equal to I but less than I plus 1. Greater than or equal to I but less than I plus 1. Box of, if I is an integer, box of x equal to I would mean X must be greater than or equal to I but less than I plus 1. Yes or no? If I said box of X is less than I, if I said I is an integer and box of X is less than I, that means box of X is less than I. That means box of X could assume values like I minus 1, I minus 2, I minus 3, and so on and so forth. Box of X could assume values like I minus 1, I minus 2, I minus 3, and I minus 4, etc. These are all permissible values of box of X, right? Now, when is box of X equal to I minus 1? When X is less than I, greater than I minus 1, right? This happens when X is less than I, but greater than or equal to I minus 1. When X lies somewhere here, box of X will be I minus 1. This is I minus 2. When is box of X equal to I minus 2? When X is less than I minus 1 but greater than or equal to I minus 2. That means box of X can assume values like I minus 1, I minus 2, I minus 3 as long as X is to the left of I. As long as X is to the left of I. That means box X less than I would mean X less than I. X could be I minus 1. Yes or no? X less than I. Then box of X could be I minus 1 or I minus 2. In each case, box X will be less than I. So box X less than I would mean X less than I. Huh? But if I said box X less than or equal to I, then X could have a value here also. All that is important is X less than I plus 1. No? This would mean X less than I plus 1. Because X could lie here, then box of X is I. X lies here, box of X would be I minus. In each of these cases, box X will be less than or equal to I. So sorry. So sorry. See, I want box X less than or equal to I. Okay, this is fine. X has to be less than I plus 1. This is fine. Right? So box X less than I would mean X less than I. Box X less than or equal to I would mean X less than I plus 1. If I said box X greater than I, that means box X could assume values like I plus 1, I plus 2, and so on and so forth. When is box of X equal to I plus 1? When X lies somewhere here, then box of X will be I plus 1. It includes I plus 1, right? That means every time X is I plus 1 and to the right, box of X will be greater than I. Yes or no? That means box X greater than I would mean X greater than or equal to I plus 1. Do you understand all of this? Independently explore also. If you are a little unsure about what I said, check this all by yourself. Two properties of box functions which are very rampantly used, but as of now I will not offer a proof for these properties. I will come back to the proof at a later point of time, but the two properties we will use time and again. One, okay, so if n is a natural number, the property number 1 that I am talking of is box of box X by n, box of box X by n will be the same as box of x by n. That's one property. The second property, which is actually very commonly used, that's going to be box of nx. N is a natural number. This one specially is very, very commonly deployed. Say for example, box of x plus 1 by 3 plus box of x plus 2 by 3, that will be the same as box of 3x. We will come to a formal description of the same later, but as of now I want you to keep this at the top of your cranium. Right then, so with a session already spent on trying to understand few basic functions like the modulus function, where I told you, there was a change in behavior, and at a certain point, wherever there was a change of sign associated, there was a prospective change of behavior. Then we got familiar with the box function or the greatest integer function, which produced an output which was always an integer. And we looked at the graph also of box x and some of its properties, namely I told you box x will always be greater than x minus 1 but less than or equal to x, right? And box x plus box of minus x would be 0 when x is an integer and equal to minus 1 when x is not an integer. What happens if box x greater than n is an integer, less than n, and so on and so forth. And two other properties which I said I will not establish right now. Box of box x by n is box of x by n. And another property which I said box x plus box of x plus 1 by n plus box of x plus 2 by n plus box of x plus n minus 1 by n equal to box of nx. These were two properties which I did not prove very explicitly to you, but promise that I'm going to come back to it when the time is right. Now, having said this, let me introduce yet another function which would constitute, let's say, foundation of our digressions in our journey of calculus. Say, if x is any real number, then either x will coincide with the integer I, right? X will either be an integer I or will lie sandwiched between two integers I and I plus 1. Two consecutive integers I and I plus 1, right? If now this I was referred to as box x. This I was referred to as box x. Right? Now, this distance between box x and I is this. This is the distance between x and box x. Yes or no? This distance d, which is the distance between x and box x, that is x minus box x, because box x will always be, can never be to the right of x can never be less than box x. So x minus box x is the distance between x and the integer to its immediate left, right? This will never be negative. This d will never be negative. It could be equal to 0, because if x coincides with I, then box x will be equal to x and d can be 0. D can be 0. So d is always greater than or equal to 0, right? Now while x floats between these two integers, right? This length is 1 unit, right? So this distance can never exceed 1 unit, will always be less than 1 unit. So this d will always be less than 1. This d will always be less than 1, yes or no, right? This d is called the fractional part of x. This d is called the fractional part of x. is called the fractional part of x and is customarily designated as curly braces around x. Curly braces around x. The output of fractional part of x will always be a number lying between 0 and 1. Fractional part of x will always be less than 1 but greater than or equal to 0. Yes or no? Right? Do you all understand this? Right? Now, let me draw the graph of fractional part of x versus x. Like I said, if I have y equal to fx equal to fractional part of x, then like I said, fractional part of x is the distance between x and the integer to its immediate left, that is box x, right? So it's defined as x minus box x, right? X minus box x. Now, when x is greater than or equal to 0 but less than 1. When x is greater than or equal to 0 but less than 1, what is box x? 0. Do you recall all of that? When x is greater than or equal to 0 but less than 1, anywhere between 0 and 1 to the exclusion of 1, the box of x will always be 0. So fractional part of x will be x. Fractional part of x will be x in this interval. So in this interval it's going to be x, right? Now, when x is greater than or equal to 1 but less than 2. When x is greater than or equal to 1 but less than 2, what is box x? 1. Box x will be 1 in this interval. So fractional part of x will be x minus 1. When x is greater than or equal to 2 but less than 3, what is box x? 2. Box x will be 2. Fractional part of x will be x minus 2. And so on and so forth. When x is now less than 0. Less than 0 but greater than or equal to minus 1. When x lies between minus 1 to 0, what is box x? Minus 1. Box x will be minus 1. And this will become x plus 1. When x is less than minus 1 but greater than or equal to minus 2, what is box x? Minus 2. And this will become x plus 2. Right. So this in this interval it's going to be x plus 2 and so on and so forth. Yes or no? This is the description of fractional part of x in various intervals, each of length 1 unit. Each of length 1 unit. And in each of these descriptions, the noteworthy point is that the left end of the interval is included in the description, but the right end of the interval is not included in the description. Yes or no? Right? Now, let's aim at drawing the graph based on this description. This is multiple lines of description. This is multiple lines of description. Which is what I said was a piecewise description, a piecewise function. In this is the piecewise description of the function, right? There is a characteristic difference in various intervals, a piecewise description, right? Let me aim at drawing the graph of y equal to fx equal to fractional part of x. I break the real number line in 1 units of interval, 0 to 1, 1 to 2, 2 to 3, minus 1 to 0, minus 2 to minus 1, and so on and so forth, right? So, zero to 1. In this, when x is greater than or equal to 0, less than 1, it goes as y equal to x. Then 1 to 2, 2 to 3, and so on and so forth, right? Similarly, on the left hand, minus 1 to 0, minus 2 to minus 1. Minus 3 to minus 2, and so on and so forth, right? Now, when x is greater than or equal to 0 but less than 1, which includes 0 but excludes 1, includes 0 but excludes 1. In that interval, it goes as y equal to x. Y equal to x is a straight line passing through the origin, making an angle 45 degrees with the positive direction of the x-axis. So, in the interval 0 to 1, which includes 0 but excludes 1, it goes as y equal to x. Now, it comes closer and closer and closer to 1, but at x equal to 1, it doesn't include y equal to x. X equal to 1 does not belong to y equal to x. And therefore, I put this hollow dot, a kink, which means that at x equal to 1, y equal to x is not the description. Y equal to x is not the description at x equal to 1. So what happens at x equal to 1? Hey, at x equal to 1, this is the description, x minus 1. That means at x equal to 1, y becomes 0, right? At x equal to 1, y becomes 0. So there is an abruptness demonstrated. It was smoothly going as y equal to x between 0 and 1, which included 0 but excluded 1. At x equal to 1, it said, all right, this is the dip that it encounters, it becomes 0. And between 1 and 2, it then went as the straight line y equal to x minus 1, which included 1 but excluded 2. And y equal to x and y equal to x minus 1 are parallel lines, right? Same slope, slope 1. So between 1 and 2, it demonstrated this. But it included 1 but excluded 2. And this description was y equal to x minus 1. At x equal to 2, what happened? At x equal to 2, it was going as x minus 2. That means it became 0 at x equal to 2. Very clearly. Very clearly, you know, every time x is an integer, its fractional part will become 0. That's why every time x is 1, 2, 3, the fractional part of an integer will always be 0, right? And then from 2 onwards, it went as y equal to x minus 2. Y equal to x minus 2 would be parallel to each of these lines. So this was y equal to x minus 2. And so on and so forth. At x equal to 3, again fractional part of x ought to have become 0. Now to the left, between minus 1 and 0, it was going as y equal to x plus 1. Minus 1 was included in the description, but 0 was excluded in the description. Between minus 1 and 0, it went as y equal to x plus 1. Y equal to x plus 1. Yes or no? Between minus 2 to minus 1, again x plus 2, and so on and so forth. Left end always included in the description, right end always excluded in the description. And so on and so forth. This was the graph of y equal to fx equal to fractional part of x in various intervals, right? And realize that fractional part of x was x minus box x. Now box x changed behavior every time x was an integer, and fractional part of x inherited that behavior. Every time x was an integer, there was an abruptness, there was a change of character represented by fractional part of x. See, it was going all right. Moment x became equal to 1, it exhibited abruptness. And then between 1 and 2, it was going all right. Y equal to x minus 1. At x equal to 2, it exhibited abruptness. Every time x was an integer, there was an abruptness demonstrated. Between two integers, it was doing good, but at an integer, there was an abruptness demonstrated, and that character came out of box x, because box x changed behavior every time x was an integer. Right? Yes or no? Just to spell out a few more things on this. Like I said, fractional part of x will always be greater than or equal to 0 but less than 1, right? So the graph of this will be above the x-axis, on or above the x-axis, never below the x-axis, and will lie between 0 and 1 always, will always lie between 0 and 1. This is the line y equal to 1. The y will never become equal to 1. In this case, y will never become equal to 1, right? And the graph 0, 1, 2, 3, and so on and so forth. Minus 1, 0. And so on and so forth. See, it never became equal to 1. That's why you see these kinks here. Yes or no? Right? This is y equal to x, this is y equal to x minus 1, this is y equal to x minus 2. These are all a bunch of parallel lines with slope 1. Right? These are all 45 degrees. And so on and so forth. Now, one simple thing which you can establish using similar triangles. At a given x, if this is a given x, see, this triangle is identical to this triangle, right? At a given x, this length would be fractional part of x, isn't it? This length will be fractional part of x. Now I claim x plus 1 will lie somewhere here, isn't it? Because this is less than 1, x plus 1 will lie somewhere here. This length will be fractional part of x plus 1, isn't it? All the y's will be fractional part of these numbers. Now, you should be able to independently establish similar triangles that this length is the same as this length. Fractional part of x is the same as fractional part of x plus 1. Using ordinary geometry, fractional part of x plus 1. And similarly, fractional part of x plus 1 will be the same as fractional part of x plus 2. Is the same as fractional part of x plus 3. Is the same as fractional part of x plus any integer I. Any integer I. Very clearly, na? Think about it. Fractional part of 0.2 is how much? 0.2? 0.2? Is this not the same as fractional part of 1.2? If you increase this by 1 unit, then the fractional part of this will also be 0.2. This will be the same as fractional part of 2.2. What's the fractional part of 2.2? 0.2. So every time you increase this quantity by 1 unit, x by 1 unit, fractional part of x replicates its value, right? So in general, in this case, f of x will be the same as f of x plus 1 will be the same as f of x plus 2, same as f of x plus any integer I. Got me? And you can also see that, see, if fractional part of x is x minus box x, fractional part of x plus 1 will be x plus 1 minus box of x plus 1. Hey, did I not tell you box of x plus an integer is the same as box of x plus I? Have I told you this? Did I tell you this? Box of x plus an integer is box x plus I. Have I mention that. So this is I, right? So this is x plus 1 minus, this is box of x plus 1. 1 and 1 will get cancelled. This will be x minus box x. But x minus box x is fractional part of x, is fractional part of x. That's an algebraic way of looking at it. So fractional part of x plus 1 is the same as fractional part of x. Yes or no? All's good? So this was just another introduction of a related function. Again, you know, it becomes imperative for me to get you introduced to all of this, although there are many more functions, but these are some basic foundation functions around which, you know, our discussions, core discussions in calculus will revolve. Another function of value and importance, not just from a mathematical standpoint, but also from a practical standpoint, engineering standpoint, which is what I'm going to introduce to you next. Can I wipe this off? Now, we have a function y equal to fx equal to signum x. SGN x means signum of x, signum x or signum of x. Now the value, the output produced by this operation depends only on the sign of x, whether it's positive, negative or 0. Signum x is defined as plus 1 when x is greater than 0. It's defined as plus 1 when x is greater than 0. When x is equal to 0, it's defined as 0. When x is minus 1, it's defined, when x is negative, it's defined as minus 1. It's defined as minus 1. That's signum of x. That's signum x. Plus 1 when x greater than 0, minus 1 when x less than 0, equal to 0 when x equal to 0. This is about, you know, in electrical sciences, electrical engineering especially, you know, when all that matters is, let's say, the direction of current in one direction and in the other direction, or no current. So let's say for all currents in one direction, that will be binarily reduced to 1 for a description. That will just tell me the direction of current. When opposite direction, I will reduce that to minus 1, and when there is no current, it could be reduced to 0. So it has practical implications. Sometimes when the magnitude of x is not important, all that is important, let's say, for example, in a current, the direction in which the current is flowing, right? Then this signum function, which has 3 discrete states, right? The output that it produces is only one of these 3, right? Based on only the sign of x, based on only the sign of x. And a very ordinary graph, therefore. At x equal to 0, it is 0. For x greater than 0, it is plus 1. So moment x is greater than 0, this is a kink. This is not a point on the graph of the function. This is a kink, right? For x greater than 0, y is 1. Again, at x equal to 0, it is 0. This is a point on the graph. And then for x less than 0, it is minus 1. For x less than 0, it is minus 1. Yes or no? This is the graph of y equal to fx equal to signum of x. And very clearly, there is a tremendous amount of change of behavior at x equal to 0. To the immediate, at x equal to 0, it is 0. To the right of 0, it is 1. And to the immediate left of 0, it is minus 1. So at x equal to 0, there is a perceptible change of character of this function. Clear? Do you all understand this?